let's begin the lecture again. Okay. There was some questions in the break as to how does this force appear, because we calculated the effect, which is only there when the projectile is moving. But I'm going to draw a slightly simpler system, which I think is used as an example in the book. That's the following. Let's see. So I have some voltage source here. And I have my rails like this. And in addition to this system here, I get a really big magnet and put it on the top and the bottom, one pole on each side. So I get a very strong magnetic field. For example, into the board like this. And as I run a current through here, the force on this one, since it's orthogonal to the field, then the force is going to be orthogonal to both. So it's, well, the magnitude of the force anyway is going to be proportional to the B field, to the length of the projectile, and the current. There you go. Okay. So now it's more easy to see because there's the same magnetic field everywhere, and but there's a real force here. Now imagine if I hold down the projectile, I just clamp it somehow. Well then, how big is the effect? Well, it's 0, because P is equal to F times dx dt, or the velocity. If I have a constant force, I mean like the force working on me from the floor, it doesn't do any work because I'm standing still, there's no movement. So that's the whole trick here, that there is a force, but there's no effect. So that explains the apparent paradox. But it's easier to, I mean, this is kind of tricky. It would depend a bit on the geometry and so on to calculate the actual force. At least it would seem like that, and it would, well. But when we relate it instead to the effect and to the flux, it's easier to get out how much energy do I get per unit time or whatever. So it's easier to get to the number. So I actually scratched my head quite a bit trying to figure this out using the forces, and I couldn't see how you can do it. So if one of you figure it out, I want to know. But using the flux is much easier, it turns out. Okay, now I think everyone saw the magnet. Has someone not seen the magnet? Well, I want to borrow it because I have a puzzle for you. And the puzzle is the following. There's some metal below here. So if I slide this around, you see that it's attracted to the metal pieces in the table. Well, if I have this magnet over here, and I let it go, let's see, I let it go, you see it slides. So there's definitely work being done, right? Now, where does that energy come from? Because when I start with the magnet far away, and then, well, far away is here, approximately. There you see. So there's some work being done. Where does the energy come from? If I do this 1,000,000 times, will I discharge the magnet? So turn to your neighbor and then discuss for a while. Is there a question? Okay, so everyone got it? I mean, most people have probably heard it, but the point is, of course, that when I'm pulling the magnet away from the point of attraction, it's basically me adding energy to the system. So it's like if I'm lifting something in the field of gravity, then I'm adding energy. It doesn't discharge the Earth as a mass. Okay. And then the next topic is inductance. I guess most of you at least, not all of you, but most of you have the course More Technique this semester. And there you probably play around with circuit elements, and inductance is one of them. But now, where's the physics in an inductance? Where does the inductance indeed come from? And that we're going to look at now. And well, we consider two loops to begin with. Loops of wire. Like this. I call this number 1. And there's a different one over here. Call that one number 2. And there's a magnetic field being generated from a current in this one. So this I1 generates a magnetic field. Let's call it B1. And some of the magnetic field lines actually run through loop 2, so to speak, and generate a flux through it. Now there's of course going to be some interaction here, because if I change the current as a function of time, say, then the flux here is going to change, and changing flux means electric force, meaning current, and so on. So there's some interaction, and we're going to try to quantify how big is this interaction. How do you figure something out about this interaction? So okay, maybe I'll write down some keywords. I1 causes B1, causes flux in loop number 2. And now let's try to determine the flux phi 2. So what's the flux in phi 2 when I turn on some current I in loop number 1? And let's see. Okay, first of all, I need B1. And that's basically just using the Biot-Savart law and integrating over all the small line elements here. And the integral looks like this. You can find this in Griffiths if you're wondering. Let's see, I1. And it's dl1 cross r hat. So, what are these? dl1 is just a small line element here. I'm going to make a new sketch, I think. So I have a small line element down here. There's a current I. I'm looking at, let's say, well, the B field at any point, maybe this point, for example. And there's an origin, as always. And this is R vector. This is R prime. And the distance here is R minus R prime is equal to big R. Okay, so I'm just looking at a point in space. I might write B of R. And of course, it's not going to matter where I put the origin. It's just going to matter the difference. That's why we only have the difference in the integral. Difference between those two positions. Okay, and this is hard to calculate in general, but I will make some, if I write down the integral for the flux now, we'll try to make some observations. Now the flux in loop 2 from the current running through loop 1 is equal to ds2. This is a small surface element in the surface enclosed by loop 2 times B1. Okay? And that's mu naught over 4 pi I1. Basically the proportionality constant. And now the geometrical factor, ds dot B1, and I insert the integral. dl cross r hat over r square. And, well, when all is said and done, this is going to be proportional to I. And all the stuff that's not proportional to I is going to be either some sort of constant, like mu naught, and this geometrical factor. So depending on how I place my, let's see, this dl1 and ds2. Now, as we have dl1 and ds2, this is basically the geometry of these two loops. So if I bend them or move them, then this geometrical factor here is going to change. And now I would like to define the mutual inductance between the two loops as the following. M21 times I1. Let's see, and this phi 2. So I have a current running in loop 1. how much flux do I get in loop 2? Well, then there's just a proportionality constant called mutual inductance that tells me how big is the flux. This is a geometrical factor. So it's a purely geometrical factor, and well, there's always a mu or a pi floating around, but those are constant. So this is just some geometrical factor saying where did I put my loops, and what's their size, their angles, so on. All of this is put into the m factor. Okay, and now we're going to make some observations. Let's see. Let's see, yeah. There's one more observation I'd like to make, and that's that if I change the numbering, from 1 to 2 here and 2 to 1 here, then there's nothing that actually changes. Well, I will show that in a second maybe more rigorously, but you'll see that there's no change in m, so to speak. So m 2 1 is equal to m 1 2. So I can just call it m in the end. And now let's try to show that a bit more in detail. Okay, so let's try to calculate phi 2, because then we can find how to calculate m21, or just m. And by the definition we have, that it's the surface integral over loop 2 dot B1, the field from loop 1. And that's, let's see, it's ds2. I'll try to get this on the vector potential form now, because we remember that it was easier to get an integral expression for the vector potential than the magnetic field, because in the vector potential there was no cross products. So that's nice. So let's try to get in the vector potential. So I just say that, well, B1 is equal to the curl of A1. And just a second. And again, we use the Stokes theorem to show that this, again, can be written as a line integral. This is around loop 2. Dot A1. And I can show, we discussed this before, that A1 is given by just an integral over the current from loop 1. Let's write that down. There's a prefactor with the current and the 4 pi. And then there's the geometrical factor. Again, this is the distance from the point I'm interested in finding the vector potential at, and the variable of integration which runs over the whole loop. And if I insert this up here, well then, can we make some more observations? Let's see. So phi 2 is equal to, just make a number 2 here to signify loop 2. dl2, that's this integral. Then the a. There you go, that's the full expression. This is of course just constants which I can move outside. So I rearrange. There's two loop integrals. And then there's the dot product of the line elements over the distance between them. So now this r minus r prime is of course just the distance between the two line elements. So it's dl1 and it's dl2, and then this is r vector minus r vector prime, and the r prime became the position at the line element when I changed this from a surface to a line integral, right? Okay. And this should be equal to I1, that's this guy here, times M21. Okay, so now I can just read off what's M21. There you go. As you can see now, the inductance only depends on the geometry of the loops and well, the distance between them. So as you can see, it's a purely geometric factor. Well, okay, there's I forgot, but there's mu naught or 4 pi. But then those are just constant of this universe, right? So this is a geometrical factor which links the interaction between the two loops, and this is known as the Neumann formula. Okay, and now I can make the following observation, which proves the previous claim I had that this is independent. I mean, if I write M21 or M12, that's the same, right? Because I could just change the numbering on the DLs and the integrals. So it looks exactly the same if I change the two. And I can also change the order of integration here. So it's a purely geometrical factor, and it's independent of, let's say, well, it's the same, it's symmetrical. If I'm looking at the interaction from this on this, or the opposite, the result is the same because of this symmetry. All right. This also means, of course, that the flux phi2 due to I1 is the same as phi1 if I2 is equal to I1. Okay? Maybe I should write that down because it's kind of confusing when you say it. So given I1, we get phi2, right? That's the definition. Now if I insert instead I2 is equal to I1, what's then the flux in loop? Well, I introduce a current I2. What's the flux in loop 1? It's the same because of this symmetry property. This is not exactly an intuitive result. For example, if I make one loop here and one over here, that's smaller, maybe tilted a bit. Well, if I run some current through here, I get some flux here. That's okay. But if I run the same current here, I would get the same flux in this one as I got in this one. That's not exactly intuitive, at least not to me. So that's something to think about while I wipe the board for the next topic. That's self-induction. Does anyone have a question on the inductance? I hear there's some discussion. Nothing? Okay. Okay. Well, if I have, let's say I just have one loop. One loop of current here. If I introduce some current on this loop of wire, well, then there's going to be a B field, so I'm going to get a flux. The loop is going to induce a flux in itself. And this is called self-induction. And it's not called M, but it's called L. And this is the inductance you typically see in a circuit, right? You have some inductance somewhere, and then how does it respond to time-varying currents? That depends on the induction L. But you can also have this coupling between two coils or two loops of wire. That's very commonly used as well in voltage transformers, for example. Now, if you look at this then, we have that phi is equal to L times I. Okay? And if I take the time derivative, I get that epsilon is equal to minus L di dt. Okay? Now I'm, of course, assuming that the loop is staying the same at all times. And so it's the time derivative of the current will give me a voltage. And this is what coils is used for, right? If you want... I guess you have better examples in your more technique course anyway, so I won't go into that. Anyway, to get the units of this, let's see. The units of the inductances are the same, and they're called H or Henry. They can be written as volt second or ampere or omega, ohms second. The second, of course, comes from that we have a time derivative, so which you don't have in the Ohm's law, so that's why you get ohm second. So that's maybe a nice way to remember the units of the inductance. And phi has the unit Weber, or Tesla times meter square. There you go. And just as a side comment, an inductance of 1 Henry, that's quite immense. That's a huge inductance. I guess you can find that by, look at that by inserting some numbers and see what are the time constants, for example. And if you have 1 Henry inductance, it's not something you can find in the ordinary school lab. Okay. So I think it's going to be the last example today is going to be the Betatron accelerator. So let's see. And the Betatron accelerator is an early design of a particle accelerator, which uses inductance as the driving force of acceleration. I just discovered this example last night, so I hope it's not full of holes, but we'll try anyway. Let's see. So, first of all, I built myself a vacuum chamber. And this vacuum chamber is also an electromagnet, or there's some electromagnet somewhere here. And thus we create a magnetic field inside this vacuum chamber. And now if I insert an electron into here, it will start to circulate around the magnetic field lines, as you've probably learned before. Well, it's just centrifugal force balancing magnetic force. Small sketch of principle. You have some magnetic force pulling it in towards the center. So this is, well, if I take this orbit, it's going to be tilted like this, spinning around in my Betatron accelerator. Okay, and now if I well, this is basically a loop of current, right? Because there's some electron flowing here, in the other direction, in fact. There's an electron, or several electrons, if you want to do something serious. There's several electrons flowing around, so it's basically a loop of current. And now if I change the magnetic field as a function of time, well, then I'm going to change not only the flux, but it's going to accelerate the electrons, because there's going to be an electromotive force. And let's see. What did I do here? There's no integral. Epsilon is equal to I don't remember exactly, but it looks right anyway. So I integrate no, this is the okay, I'm just going to do what's in the notes, but I don't remember why it's correct. But we're going to see if we get something out of that. Okay, 2 pi times rho, and rho is the distance from the center to the, well, it's a radius of the circular trajectory. And it should be equal to, well, yeah, this is from the Stokes theorem. That's right. Okay, so it's pi squared rho dB avg dt. Okay, so the time derivative of the magnetic field times the area, that's going to be the induced electromotive force. So I get epsilon 1/2 rho dB average dt. And so how much? So what happens is I get some electrostatic accelerator to give the electron some initial speed, and I inject it into the accelerator. And well, this you can do with, let's say, van der Graaf accelerator. This is actually a technique for a way of doing it today, to get the electron starting. And then I have a magnetic field and I start ramping it. And that's because there's a time derivative term here. Then it's going to accelerate the electrons, as well as when the electrons accelerate, they're going to get a larger velocity and a larger momentum. but as the electrons accelerate, also the magnetic field grows in strength. So as an approximation now, let's just keep rho constant. Hopefully those will cancel out. So if you look at Newton's second law, the time derivative of the momentum of the electron should be E times, yeah, that's right. This is not, that's why. This is not the electromotive force, it's the electrical field. Which is, of course, the same thing. Well, this is then the big epsilon. That's where things went wrong. Okay. So it's the accelerating force is just the charge of the particle times the electrical field, which is tangential in this case. Okay. And I can insert my expression for the electrical field, which is right here. And I get half rho E dB dt. I'm not going to bother calculating B average because in general that might be quite complex and will depend on how you design your accelerator, which also has to do with the focusing of the beam and a lot of other stuff we really don't have time to go into. So when I just integrate this, we get that the P final, the final momentum of the electron, is going to be half E rho B average. And this was, this was a technique that was actually used early on in particle accelerators, like in the 40s, 50s. Was a topic of research. At some point in time, these were among the biggest accelerators in the world. But as people wanted to build bigger and bigger accelerators, well, of course, you need a bigger and bigger vacuum chamber, so that's inconvenient. Also, this is a so-called weak focusing synchrotron because there's some variation in the magnetic field over here, right? And if you do that just right, you might get it to focus slightly so that the beam is transversely stable, meaning that if I insert a beam of electrons here, it will keep circulating. If I sort of perturb it slightly, it will still keep circulating, right? It's like balancing an egg. It has one stable equilibrium and one unstable. So you have to make it a stable equilibrium, otherwise the beam is just going to fly into the walls and you won't have a particle accelerator, you'll just have a piece of crap. And so this is important. And so the biggest modern day accelerators are all synchrotrons. And they use separate acceleration and focusing magnets. Well, the acceleration is done by electrical fields that vary in time, and the focusing is done by magnets, so you can actually sort of tune how big you want the beam at certain positions around the accelerator, and you don't need a huge vacuum chamber, because if you want to build a kilometer-sized particle accelerator, you can't build a vacuum chamber that big. Well, if you want to try, good luck, but you're not going to be able to do that. Okay, so we have time for one more comment I'd like to make, and that's the simplest possible application of induction. I'm really hoping you've seen this before, but I'm going to say it again just so you know about it, and that's the voltage transformer. So this is an iron core. Let's see. Of the transformer, and I insert some coil around here. And there's a time-dependent current, like the current you got in the wall socket. And well, let's say that this is the high voltage grid, which is the large power lines you see around all over the country. And then on this side I'm going to put 220 volts. So there's N1 loops here, and N2 over here. And over here I put some light bulbs or whatever I have in my home. And now the relation between the voltages is the same as between the loops. Let's see. There you go. So if V1 is, let's see, if N1 is small compared to N2, then the voltage is also going to be small. And as a small homework, well, first, the idea is to get the same flux in these two. So all of the flux lines I generate with this coil, I'll try to get into this coil for maximum efficiency. That's why you put this iron core, because now the magnetic flux lines is going to flow through here. As we remember, a ferromagnet is a very strong magnetic amplifier, so to speak. So because we bend it around, the magnetic flux lines will bend around as well. And hopefully keep all of the flux line aligned. So we get all of the flux from N1 into, no, loop 1 into loop 2. And now I have a small suggestion for something to think about for next week, because now you have several days. It would be boring if you didn't have anything to think about. So why doesn't this violate energy conservation? So I hope some of you will have the answer by Monday. It's not too hard, but well, you can get some hints in the book. And as another comment, this is one of the most efficient machines known by man. You can actually get transformers that are more than 98% effective, even when using standard ferromagnetic cores and so on. This is called a core of the transformer. Okay. So if you make them superconducting, you can get 99.9% or something like that. It's really quite impressive compared to a lot of other stuff that people made, which is, well, a lot less efficient. Just think about your car or your own digestion. Okay, so I'll see you on Monday, unless someone has a question. Okay.